Okay, now it's time to talk about how electricity and magnetism are related to each other. In other words, how magnetism can be used to produce electricity and how electricity also produces magnetic fields. So, here we go. We're going to start pretty simple and talk about how a magnetic field could produce an electric current in a complete circuit. So usually it's a loop of wire, but I'm going to simplify things just a little bit and show you a portion of a wire that's currently straight in between two magnetic poles. So we're going to start with this just to get the idea. Now there's two really crucial concepts to grasp what we're going to be talking about here, and they're written right here on the slide. And it's called, basically this first part is that magnetic fields produce electric current under certain circumstances. They can, but they don't automatically produce electric current. And then any current that's flowing through a complete circuit will produce a magnetic field around itself. So this always happens. This sometimes happens under the right circumstances. So let's talk about how you can cause an electric current to be produced by a magnetic field. We'll start there. Okay, so off to the side here, you're going to notice there's this little picture of a hand, and that was in the other diagram as well. You're going to have to mentally kind of shift this hand around sideways a little bit. It's really hard to do three-dimensional on a two-dimensional screen. But basically, this is called the Flemings right-hand rule for a dynamo. You don't have to worry too much about this specific term, but basically you're going to set your hand, if you want to figure out what's going on in this situation here, you can set up your hand like this with your three fingers all at right angles to each other. It's like a 3D axis, like an XYZ three-dimensional graphing axis. So your thumb is pointed up, your index finger is pointed at a right angle to it, and then your middle finger is pointed at a right angle to both of them, sticking outwards. So it looks like this. And this will tell you what's going on in that straight wire right there if we move it. All right, that's the key thing. Magnetic field can induce a current if the conductor is moving inside the field. And additionally, it has to be part of a complete circuit. All right, so it will not induce a current in just a piece of wire that's not connected to anything. The wire has to be in a circuit. All right. So that's why I've got a mark here, in from the rest of the circuit, out to the rest of the circuit. All right, we just didn't draw it in this particular case. So let's say that we move the wire upwards through the magnetic field, so the direction of motion is in the direction of your thumb. We're using some kind of, like, say that you physically just grab the wire and move it upwards, like that. Or maybe it's attached to something that's moving it up. In any case, something is physically moving the wire upwards between these two poles of the magnet. Now you might remember that the direction of the magnetic field goes from north to south, so the magnetic field is going this way, and we usually represent magnetic field with a B. So the magnetic field is going that direction, so that is represented by your index finger, so you would point your thumb upwards, point your index finger that way, and if you do that right now in front of your screen, just do that. Thumb pointed upwards, finger pointed toward that south pole. Now if you stick your middle finger out, you'll notice it's pointed straight at yourself. So the direction of the current flow in this wire that's caused by the upward motion would be out of the screen towards you, three-dimensionally. All right? That's the concept. Basically, if you move a wire through a magnetic field, you will cause current to flow, and the direction that the current flows depends on which direction you move the wire. So how could we actually see this happen in an experiment? Well, basically you could hook up, like we had said, there was a complete circuit, we just hadn't drawn it in the other diagrams. Now I've drawn in a complete loop of wire and we've attached an ammeter. The ammeter will measure current. So if this loop is, if the complete loop, but if this part of the wire in here is stationary, then you're going to have a 0 reading on the ammeter. If you have the wire moving up, you're going to have a reading that corresponds to current going this way, which we just talked about. The current will be flowing in this direction, which I guess that's what? Counterclockwise. Then if we were to move this thing downwards, down in the field, well, then you'd have to point your thumb down, and you'd still have to point your first finger in the direction of the magnetic field. So let me just pause and draw this in. Okay, so I've drawn in the F and the B representing the magnetic field. So if you were to point your thumb downwards and then point your index finger in the direction of the magnetic field, so you're going to have to turn your hand upside down, right hand, keep in mind right hand, then your middle finger should be pointed at your screen. So that shows you that if we move the wire downwards, the current is going to go this way, so opposite. All right? So that's what's going to happen, and then that, of course, would be on the ammeter. You would read the opposite of if you were moving it upwards. So that's the idea there. So you could see this happen if you hooked up a wire to an ammeter in a complete circuit and then moved the wire up and down. When the wire is stationary, the ammeter will be on 0. When it's moving up, the ammeter will be positive, or it will turn to one side. And then when it's moving down, it will be negative and it'll turn to the other side. Alright, all just depends on how you define your terms. So let's move along. How can we affect the induced EMF? How could we make it different? And this, we'll just run through this really quick. There are several ways. If a longer portion of the conductor is in the magnetic field, then you'll get a larger EMF. So basically, if you have a wider magnetic field and put more of your wire into it, then you get more EMF. If the conductor is moved more rapidly, so move it faster, then the EMF is bigger. But of course, the conductor will move through the field faster, so the time of the EMF will be shorter, but the size of the EMF will be bigger. Also, if you make the magnetic field stronger, then the induced EMF will also get stronger. That's fairly obvious. So those are 3 ways of changing the induced EMF or making it stronger. Now it's time to mention what's called Lenz's Law. And you need to be aware of this, but it is pretty complicated, so bear with me. When an electric current is induced in a conductor that experiences a changing magnetic field, the direction of the induced current will always act in such a way to oppose the change that induces the current. It sounds really complicated, but basically, as we're about to say in a minute, current flowing through a wire, which we already mentioned, when current flows through a wire, it produces its own magnetic field, always. So by moving this wire through the magnetic field, we produce a current. That current is also going to produce its own magnetic field. And it will produce a magnetic field in such a way that the wire is going to experience a downward force due to the magnetic field produced by the current. So we're moving it upward physically, but then the current that's produced in there is going to try to move it downward. Obviously, we're going to be pulling up harder than the current is going to be pushing downward, but the stronger the current we make in this wire, the stronger it's going to try to work against what we're doing. It's a strange concept, but let's just zoom in on this picture here, get a better idea of what we're looking at. So I believe this diagram is reversed from the other magnetic fields that I had shown here. So in this case, if you use your right-hand rule, you should get a current going that way. It's not that important, actually, exactly which way the current is going in this picture. The key idea is that the force that's produced by the EMF itself, all right, so say the current is flowing that direction, which I think would happen in this situation. If you follow that rule, right hand thumb up, and then in this case, your index finger should be pointing from north to south. So thumb up, index finger north to south, then your middle finger should be pointing into screen. So the current would be flowing this direction into the screen. In any case, that current flowing that direction in this magnetic field would produce a downward force on this wire. So the downward force is not stronger than the force we're applying to move it, but it will act against our moving of the wire. So basically, when we induce a current in a conductor by moving it through a magnetic field, that induced current will act against what we're doing and try to prevent the motion through the field. All right, that is Lenz's law of induction. You need to be aware of that. So let me just zoom out one more time so you can see it. And we'll move on to the last slide for this video. All right, and we're just really quickly going to mention, because this is a pretty simple concept, as we've been saying, current flowing through a conductor produces a magnetic field. And that's what this diagram shows. This is a conductor, say a wire, a straight wire, and we're going to have current flowing through it. So again, we have a different right-hand rule this time. You cup your fingers around just like this shows and point your thumb up. If the current is flowing in the direction of your thumb, then the magnetic field curls around in a circular pattern around that straight wire, just like this, in the direction that your fingers curl. So if your fingers curl this way, that is the direction of the magnetic field. Alright, you could try it again on this image if you'd like. Point your thumb this way, and your fingers will curl around that way. Alright, so that's about it. A straight wire will produce a circular field of magnetism around it if the current is flowing through it. And that's it. Current flowing produces a magnetic field, always. So, and you can figure out which way the magnetic field goes by this right-hand rule. That's it for this video. We'll move on and do a lot more with these concepts in future videos and with stuff in class. All right, thanks for watching. Hope it was helpful, and we'll see you next time.